There are structures inside your body that have not changed since before the Earth existed. Not metaphorically, not approximately. The nuclei of carbon, oxygen, and iron atoms sitting inside you right now were forged inside stars that lived and died before our solar system had even begun to form. They survived the collapse of those stars, the violence of supernovae, billions of years of drifting through interstellar space, the formation of this planet, the entire history of geology and oceans and life, and they arrived here, inside you, completely intact. The nucleus at the center of each of those atoms is the same bound cluster of particles that came out of a stellar core more than 4 billion years ago. It has not changed. That is not a poetic way of saying matter is old. It is a precise claim about structural persistence. The nucleus, specifically, is what held. Not the atom as a whole. Electrons get exchanged constantly. Atoms cycle through molecules, through air, through water, through other bodies. But the nucleus sits at the center of all of that cycling and refuses to come apart. Hydrogen nuclei that formed in the first few minutes after the universe began are still intact. The stability is not occasional. It is not conditional. It is so total and so reliable that it underlies every solid object you have ever touched, every chemical reaction that has ever occurred, every structure that has ever held its shape. Chemists do not wonder whether the nucleus will hold. Biologists do not factor in the possibility that the carbon in a protein might suddenly disaggregate. The stability is simply assumed because it has always been there, quiet and absolute, underneath everything. But take one step closer and the picture changes. The nucleus is not calm the way a resting object is calm, where nothing is pushing and nothing is resisting. It is calm the way a structure under enormous opposing loads is calm, where stillness is not the absence of force, but the precise cancellation of forces that individually would be catastrophic. The density alone signals that something is wrong with the simple picture. Nucleons, which is the collective name for protons and neutrons, are packed into a region roughly 100,000 times smaller than the atom that contains them. At that density, the forces between them are not negligible. They are not background noise. They are the entire story. And one of those forces, operating at that distance between particles carrying the same charge, should be tearing the nucleus apart right now. So why isn't it? If you like exploring questions like these, feel free to leave a like and subscribe. And if there's something about the universe you find yourself wondering about now and then, share it with us in the comments. It might become the next question we will explore on this channel. For now, let's get back to that question. That question does not have a simple answer. It has a descent, and it begins with a force that should have already won. Every proton inside a nucleus carries a positive electric charge. That is not a detail. It is the central tension of everything that follows. Because the electromagnetic force, the force that governs how charges interact, has one absolute rule. Identical charges repel, always, without exception. And the repulsion is not gentle. It does not fade politely at short distances. It scales with proximity. The closer two positive charges are to each other, the harder they push apart. Bring them very close, and the force between them becomes very large. Bring them close enough, and the force becomes enormous. Now consider what a nucleus actually is, not abstractly, but geometrically. A collection of protons, anywhere from 1 in hydrogen to 92 in uranium, packed into a space so small that if an atom was scaled up to the size of a football stadium, the nucleus at its center would be roughly the size of a marble. Every one of those protons is sitting inside that marble, separated from every other proton by distances that, by the standards of the electromagnetic force, are essentially zero. At those separations, the repulsive force between any two protons is not a background condition. It is an active, continuous, extraordinarily powerful push outward. You can get a feel for the scale of it this way. The electromagnetic repulsion between two protons separated by a typical nuclear distance is on the order of tens of newtons. That is the force you would need to hold two small magnets together or lift a heavy book, expressed between two particles each with a mass of less than a billionth of a trillionth of a gram. At the scale of the particles involved, that force is not large. It is staggering. It is the kind of force that, if nothing were countering it, would accelerate those protons away from each other at rates that make any ordinary motion look completely still by comparison. And in a nucleus with many protons, every proton is being pushed by every other proton simultaneously. The repulsion does not just operate between neighbors, it operates across the entire nucleus. A proton on one side feels the push from every proton on the other side. The total outward pressure inside a large nucleus is not the sum of a few interactions. It is the accumulated electromagnetic hostility of dozens of identical charges all refusing to occupy the same space. That pressure is real. It is present right now, inside every nucleus, in every atom of every object around you. It has never stopped. It has been pushing outward without interruption since those nuclei formed. And yet the nucleus holds. Something is not just counteracting that force. Something is beating it. Something is beating the electromagnetic repulsion. That much is already clear. The nucleus holds, the protons stay bound, and the outward pressure never wins. So there must be a force operating inside the nucleus that is stronger than electromagnetism at those distances. Physicists call it the strong force, and if you have encountered that name before, you may feel like something has been explained. A force exists. It is stronger. It wins. Problem resolved. But nothing has been explained yet. Naming a force is not the same as understanding one. Gravity has a name too, and for most of human history that name sat on top of a complete mystery. The name strong force is simply a label placed over a gap. It tells you that something is there. It tells you nothing about what that something is, how it operates, what it acts on, what carries it, or why it has the properties it does. And the properties of the strong force are strange enough that the name alone actively obscures them, because the strong force does not behave like any force your intuition has already absorbed. Consider what you already know about forces at a distance. Gravity pulls every massive object toward every other massive object, and it reaches across the entire universe, weakening with distance but never fully disappearing. Electromagnetism does the same. Opposite charges attract across any distance. Identical charges repel across any distance. The force weakens as you move apart, but it is always there, always reaching, always present at whatever scale you are operating on. That is the intuitive picture of what a force does. It extends outward. It connects things across space. Its reach may be limited by distance, but its nature is to propagate. The strong force does not do this. It does not reach outward in any meaningful sense. It does not connect distant objects. It does not weaken gradually across space the way gravity and electromagnetism do. It operates only across extraordinarily short distances, distances smaller than a single proton, and beyond those distances it simply stops, not weakens, stops. A proton sitting one proton width away from another proton feels essentially nothing from the strong force. Move them close enough and the force becomes the most powerful thing in nature. That transition from nothing to overwhelming happens across a distance you could not visualize with any ordinary reference point. That behavior already tells you something important. A force that shuts off so abruptly at short range is not operating the way gravity or electromagnetism operates. It is not simply a stronger version of something familiar. It is a different kind of thing entirely. And to understand what kind of thing it is, you have to go somewhere electromagnetism never required you to go. You have to go inside the proton itself. For most of the 20th century, the proton was treated as a fundamental particle, something with no interior, no components, a point of mass and charge that simply existed as itself, irreducible, the kind of thing you hit bottom on when you kept asking what something was made of. That picture was clean, and it was useful, and it was wrong. In the 1960s, physicists began firing electrons at protons at extremely high energies, not to break them apart, but to probe them, the way you might learn something about the inside of an object by throwing things at it and watching how they scatter. If the proton were truly a featureless point, the electrons would scatter in a predictable, uniform way. They did not. The scattering patterns showed that the electrons were bouncing off something inside. Hard, localized concentrations of something, sitting within the proton's interior, deflecting the incoming electrons at sharp angles that a smooth, uniform distribution of charge could never produce. The proton had structure. It had parts. Those parts are quarks. Each proton contains 3 of them. Each neutron contains 3 of them. And the quarks inside a proton are not all the same. 2 of them carry a fractional positive charge, and 1 carries a fractional negative charge, and the specific combination of those fractional charges is what produces the proton's overall charge of positive 1. The neutron is built from the same ingredients in a different arrangement, 2 carrying fractional negative charge and 1 carrying fractional positive, which is why the neutron's overall charge is 0. These 2 quark types have names. The one with fractional positive charge is called the up quark. The one with fractional negative charge is called the down quark. A proton is 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up quark. That much is already a significant revision of the picture. The particles that make up every nucleus in every atom are not themselves fundamental. They are composite. They have an interior life, and that interior life is where the strong force actually lives. Because the strong force does not act on protons and neutrons directly. It does not even see them as its primary objects. What the strong force acts on is something that protons and neutrons carry inside them, something that has nothing to do with electric charge, something that operates on an entirely different axis of physical reality. To get there, you need to understand what quarks actually carry, and it is not anything your intuition has a prepared category for. What quarks carry has no name in ordinary experience. It is not mass. It is not electric charge. It is a third kind of charge, one that only operates at subatomic scales and leaves no trace in the world you move through directly. Physicists call it color charge, not because quarks are colored, but because the mathematics of how this charge combines follows rules loosely analogous to how colored light combines, and the name stuck. The analogy should not be pushed. Color charge is not visual. It is not metaphorical. It is a real physical quantity, and the strong force is the force that acts on it. Each quark carries 1 of 3 color charges, labeled red, green, and blue purely by convention. The rule governing them is this: the only configurations permitted to exist as stable observable particles are those where the color charges cancel completely. 3 quarks, 1 of each color, cancel to produce what is called color neutral. This is why protons and neutrons contain exactly 3 quarks. Not because 3 is convenient, because 3 is the minimum arrangement that satisfies the charge accounting. The nucleus is built from 3s because the underlying structure requires it. The force between color charges is carried by particles called gluons. When 2 quarks interact through the strong force, gluons pass between them, transferring color charge continuously. Inside a proton right now, quarks are exchanging gluons in a dense, uninterrupted flow that never settles. But gluons are not simply the strong forces equivalent of photons, the particles that carry electromagnetism. There is one difference between them that changes everything. Photons carry no electric charge. Two beams of light passing through the same point do not deflect each other, do not interact, simply pass through. The carrier of electromagnetism is invisible to electromagnetism itself. Gluons carry color charge, which means the strong force acts on gluons. Gluons interact with other gluons, and that single fact, a force whose carriers are subject to the force they carry, is what determines the geometry of everything that follows. When an electron and a proton attract each other electromagnetically, the field between them spreads outward in all directions. It dilutes with distance. That dilution is precisely why electromagnetic force weakens as separation increases, why it becomes negligible across large scales even though it never fully vanishes. Nothing pulls the field back. It is free to expand. The gluon field between two quarks cannot do this. Because gluons interact with each other, the field lines do not fan outward. They pull each other inward, self-attract, and what forms between two color charges is not a widening field, but a narrowing tube. A concentrated strand of gluon field that maintains roughly constant energy per unit length as it stretches. Pull two quarks apart, and this tube stretches with them. The energy stored in it grows steadily. The force does not weaken with distance, it holds. At some point, the energy stored in that stretched tube reaches a threshold, and here the mechanism does something that has no parallel in electromagnetism. Rather than allowing the tube to stretch indefinitely, the accumulated energy spontaneously produces a new quark-anti-quark pair directly out of the field itself. The tube snaps. New quarks appear at the broken ends. What began as an attempt to separate two quarks has instead produced two new bound systems, each color neutral, each complete. The original quarks are still confined. They simply have new partners. This is not a wall preventing escape. It is a mechanism that converts the energy of escape into new confinement, which means the question of how hard you push is irrelevant. Every collider ever built, accelerating particles to within fractions of a percent of light speed, has produced the same result when directed at quark separation. Not free quarks, sprays of new bound states, more hadrons, more confinement. The debris of the highest energy collisions in human history is already reconfined before any detector registers it, and yet something does leak out of a nucleon, not a quark, something else, something that reaches across the gap between one nucleon and the next, and that something is what the nucleus actually runs on. Before moving to what leaks, it is worth sitting with what confinement actually means for the mass of the nucleus, because there is something deeply counterintuitive sitting inside everything said so far, and passing it without noticing would leave a gap in the foundation. 3 quarks inside a proton, their combined rest mass, the mass you would assign to each quark if you could somehow isolate and weigh it, accounts for roughly 2% of the proton's total mass. 2%. The remaining 98% is not matter in any conventional sense. It is energy, the kinetic energy of quarks moving inside the confinement boundary, the energy stored in the gluon field threading between them, the ceaseless churning of quark-anti-quark pairs, flickering in and out of existence within the nucleon interior, what physicists call C-quarks, borrowing energy from the field momentarily before annihilating back into it. The proton is not 3 quarks sitting still inside a boundary. It is a dynamic system in which 3 quarks, to distinguish them from the transient C, move continuously through a dense medium of gluons and ephemeral quark pairs. The boundary is not a wall. It is a consequence of the flux tube geometry. The same self-attracting gluon field that prevents separation also defines the region within which this activity occurs. What this means is that when you hold something, the mass you feel in your hand is overwhelmingly not the mass of quarks. It is the mass equivalent of confined energy, of motion that cannot escape, of a field folded back on itself so completely that it registers as substance. The solidity you felt running your hand across a surface at the very beginning of this, that resistance, that weight, is almost entirely the frozen energy of confinement, not particles, process. And that process, sealed inside each nucleon, still has to reach across to the next nucleon somehow, or the nucleus itself would never hold. The confinement that operates inside a nucleon is total. The flux tube geometry seals it. The gluon field folds back on itself. The quarks inside a proton are as bound as anything in nature can be bound, and the energy of that binding is what gives the proton most of its mass. But a nucleus is not one proton. It is many. A carbon nucleus contains 6 protons and 6 neutrons sitting within a space so small that the surface of one nucleon is essentially in contact with the surface of the next. And the force that binds quarks inside a nucleon, that total self-sealing, confinement regenerating force, does not straightforwardly extend to bind nucleons to each other. This is not obvious. If the strong force is powerful enough to permanently confine quarks, the intuitive expectation is that it should also handle the comparatively modest task of holding protons and neutrons together. But the strong force, strictly speaking, acts on color charge, and nucleons are color neutral. The color charges of the 3 quarks inside each nucleon cancel completely. From the outside, a proton does not present a color charge for the strong force to grip. It is, in the language of the force, invisible. The situation has a loose parallel in electromagnetism. A water molecule carries both positive and negative charges, but they cancel, and the molecule as a whole is electrically neutral. From a distance, it presents no net charge, and the electromagnetic force has nothing to act on. But get close enough, and the internal charge distribution becomes detectable. The positive and negative charges are not perfectly overlapping. They sit in slightly different positions within the molecule, and at short enough range that asymmetry becomes significant. A neighbouring molecule feels not the net charge, which is 0, but the uneven distribution beneath it. The result is a weak residual interaction between neutral molecules, not the full electromagnetic force, but a pale echo of it leaking through the overall neutrality. Something similar happens between nucleons. The color charges inside each nucleon cancel overall, but the quarks carrying those charges are not points. They occupy space. They move. Their color charge distribution is not a perfect geometric cancellation at every instant. At the distances where nucleon surfaces are essentially touching, that imperfect cancellation becomes significant. Something leaks through, not the full strong force. A residual, a pale echo of the underlying color interaction, reaching just far enough to grip the neighboring nucleon and pull it in. That residual is what the nucleus runs on, and its nature, what carries it, how far it reaches, and why it has the range it does, is what determines every structural feature of nuclear matter. The residual interaction between nucleons is carried by particles called pions, not gluons. Pions are composite particles, each one built from a quark and an antiquark bound together, and they are the lightest particles the strong interaction can produce. That lightness matters enormously, but before getting to why, it is worth understanding what pion exchange actually means mechanically, because the word exchange can create a misleading picture if left unexamined. It sounds like two nucleons are tossing something back and forth the way two people might throw a ball between them. That image suggests the pion travels as a distinct observable object moving through the space between them. What actually happens is subtler. The quarks inside a nucleon are in continuous motion, fluctuating constantly in their spatial arrangement. That internal activity occasionally produces a quark-antiquark pair at the nucleon surface, a pion that briefly exists outside the confinement boundary of its parent nucleon. That pion does not travel far. Its existence outside a bound state is inherently unstable, and the only way it resolves that instability is by being absorbed. If a neighboring nucleon is close enough, the pion reaches it, is absorbed into its quark structure, and the entire transaction constitutes an interaction between the two nucleons, a force. What makes this residual, rather than the full strong force, is the color neutrality of the nucleons involved. The pion is a neutral intermediary, moving between two neutral objects, a shadow of the underlying color dynamics, real and powerful enough to overcome the electromagnetic repulsion between protons, but operating through an indirect mechanism. Every nucleus heavier than hydrogen exists because this interaction wins at short range, and yet the force has a sharp boundary. Move two nucleons beyond a certain separation, and it drops away so rapidly it becomes effectively zero within a distance comparable to the diameter of a single nucleon. The reason for that sharp boundary is sitting inside the pion's mass. Every force carrier has a range determined by its mass. This is not an arbitrary rule. It comes from something deep in quantum mechanics about how long a particle can exist, when its existence is effectively on loan from the energy budget of the system producing it. A massless carrier, like a photon, can travel indefinitely. It costs nothing to sustain. A massive carrier has a clock running from the moment it is produced, and the heavier it is, the faster that clock runs. The pion is the lightest particle the strong interaction produces, but it still has mass, and that mass sets a hard limit on how far it can carry the residual force before its clock expires. The relationship between carrier mass and force range is precise. The heavier the carrier, the shorter the range, and the drop-off is not gradual, it is exponential. Beyond the characteristic range set by the pion's mass, the residual strong force does not weaken slowly the way gravity does across increasing distance. It collapses. A nucleon sitting just outside the interaction range of its neighbor feels essentially nothing from the residual strong force, not a weakened version of what the adjacent nucleon feels, but nothing. The transition from bound to unbound happens across a distance smaller than a nucleon's own diameter. This has a consequence that shapes everything about how nuclei are structured. Because each nucleon only interacts strongly with its immediate neighbors, adding more nucleons to a nucleus does not uniformly increase the binding. A nucleon sitting in the interior of a large nucleus is pulled by neighbors on all sides and is deeply bound. A nucleon sitting on the surface has neighbors on one side only and is less tightly held. As nuclei grow larger, the fraction of nucleons sitting on the surface grows, and the average binding per nucleon begins to change. The electromagnetic repulsion, meanwhile, does not respect the short-range limit. Every proton feels every other proton regardless of distance. In small nuclei, the residual strong force dominates. In large ones, the accumulated electromagnetic repulsion begins to catch up. That tension between a short-range attraction and a long-range repulsion is what gives the nucleus its size, its stability limits, and ultimately its tendency to behave very differently at opposite ends of the periodic table. Take the surface and interior distinction from the last segment and push it further. A nucleon sitting deep inside a large nucleus is not simply surrounded by neighbors. It is sitting inside a potential, a region shaped by the combined residual strong force of every nucleon around it. And that potential is not a smooth, featureless bowl. It has structure. Nucleons inside it do not occupy arbitrary positions or carry arbitrary energies. They arrange themselves into discrete levels, the same way electrons arrange themselves into shells around the atom, and for the same underlying reason. Quantum mechanics does not permit particles confined to a region to carry just any energy. It permits only specific values. Everything else is forbidden. This might feel like a detail. It is not. The shell structure of the nucleus is what determines which combinations of protons and neutrons produce stable nuclei, and which do not. Certain numbers of protons, certain numbers of neutrons fill shells completely. A nucleus where both proton and neutron shells are full sits in a configuration of unusual stability, lower energy, less susceptibility to decay. These numbers 2, 8, 20, 28, 50, 82, 126 are called magic numbers, and nuclei built around them behave measurably differently from their neighbors on the periodic table. Helium, with 2 protons and 2 neutrons, both magic, is so stable it almost never participates in chemistry. Lead-208, with 82 protons and 126 neutrons, both magic, is the heaviest stable nucleus in existence. A nucleus sitting just outside a magic number is a different animal entirely. One proton or neutron beyond a filled shell sits alone in the next level, only partially bound, held less tightly than everything beneath it. That exposed nucleon changes the nucleus's behavior. It affects how readily the nucleus interacts with others, how it responds to being struck, and critically, how stable it is against decay. Shell structure is not decoration layered on top of nuclear binding. It is woven into the binding itself, determining not just how tightly the nucleus holds, but whether it holds at all. Shell filling explains part of the stability pattern, but not all of it. There is a second constraint operating alongside shell structure, one that has nothing to do with energy levels, and everything to do with the balance between protons and neutrons inside the nucleus. In light nuclei, the stable ones tend to have roughly equal numbers of protons and neutrons. Helium has 2 of each. Carbon has 6 of each. Oxygen has 8 of each. That symmetry is not coincidental. Protons and neutrons occupy separate but parallel shell structures, and filling them in step keeps the total energy of the nucleus low. A nucleus with significantly more of one than the other has nucleons sitting in higher shells on one side, while lower shells on the other side sit empty. That asymmetry costs energy. Nature does not maintain it willingly. But as nuclei grow heavier, something shifts. The electromagnetic repulsion between protons accumulates with every proton added, and at some point equal numbers of protons and neutrons no longer produces the most stable configuration. The repulsion from the growing proton count needs to be diluted. Neutrons do not carry electric charge, so adding more neutrons increases the binding from the residual strong force without adding to the electromagnetic pressure. Heavy stable nuclei compensate by carrying progressively more neutrons than protons. Lead-208 has 82 protons and 126 neutrons. That imbalance is not instability. It is the precise asymmetry required to keep the electromagnetic repulsion from winning. There is a limit to how far that compensation can extend. Add too many neutrons and the neutron shell fills, while proton shells sit partially empty, creating a different kind of asymmetry that also costs energy. The stable nuclei trace a narrow path through proton-neutron space, a valley of stability where shell filling, proton-neutron balance, and electromagnetic considerations simultaneously converge. Nuclei sitting inside that valley persist. Everything outside it feels a pressure pulling it back toward the valley floor, and the mechanism through which that pressure acts is what the next layer is entirely about. A nucleus outside the valley of stability is not in a neutral condition waiting passively for something to happen to it. It is under pressure. The imbalance between its proton and neutron count, or the incomplete filling of its shells, or the accumulated electromagnetic repulsion of too many protons, creates a configuration whose total energy is higher than it needs to be. And physical systems under that kind of pressure do not simply sit. They find ways to reduce it. The ways available to a nucleus are constrained by what is physically permitted at that scale. It cannot shed energy continuously the way a hot object radiates heat, bleeding off excess in a smooth, uninterrupted flow. Energy at the nucleus scale comes in discrete amounts, and the transitions between configurations are discrete events. A nucleus outside the valley does not gradually drift towards stability. It sits, unchanged, sometimes for fractions of a second and sometimes for billions of years, and then, in a single event, it transforms. One moment, it is one nucleus. The next, it is another, sitting closer to the valley floor, having shared exactly the energy required to make that specific transition. What gets shed depends on the nature of the imbalance. A nucleus carrying too many neutrons relative to protons converts a neutron into a proton inside its own structure, emitting an electron and a neutrino in the process. The proton count rises by 1, the neutron count drops by 1, and the nucleus moves one step sideways toward the stable balance. A nucleus carrying too many protons does the reverse. A nucleus sitting in a high-energy configuration without a simple proton-neutron fix sometimes sheds an entire chunk of itself, 2 protons and 2 neutrons bound together, which happens to be the exceptionally stable helium nucleus. Each of these is a different mode of decay, and each one is the nucleus doing the only thing available to it, given its specific imbalance. What none of this explains yet is the timing. Why does a nucleus sit unchanged for a measurable period before decaying? The imbalance is present from the moment the nucleus forms. The lower energy configuration is available from the start. Nothing external triggers the transition, and yet the nucleus waits, sometimes for nanoseconds, sometimes for longer than the current age of the universe. The reason for that waiting is not classical. It cannot be. Classically, a system under pressure moves immediately toward the lower energy state if the path is available. The path here is available. Something else is governing the clock. Picture a ball sitting in a shallow depression on top of a hill. Classically, if the ball does not have enough energy to roll up and over the rim of the depression, it stays. The barrier is real. The energy required to surmount it is real. Without sufficient energy, the ball simply cannot get out, and no amount of waiting changes that. The barrier does not erode. The ball does not accumulate energy from nowhere. Classical mechanics is categorical on this point. If the energy is not there, the transition does not happen. A nucleus does not obey this. Not because nuclear physics is lawless, but because at quantum scales the concept of a particle having a precise position on one side of a barrier with insufficient energy to cross it is not a well-formed description of reality. A quantum particle is not a point sitting at a location. It is a distribution of probability extending through space, and that distribution does not terminate sharply at a barrier. It bleeds through, exponentially suppressed on the other side, but non-zero. The particle has some probability of being found beyond the barrier, even when it classically has no business being there. And probability, in quantum mechanics, is not a statement about ignorance. It is a statement about what is physically real. This is tunneling, not a metaphor for a process that needs a better explanation. The actual mechanism. An alpha particle, 2 protons and 2 neutrons bound together inside a large nucleus, sits in a potential well created by the residual strong force. The electromagnetic repulsion is also present, pushing outward. Classically, the alpha particle does not have enough energy to climb over the barrier created by that repulsion and escape, but its wave function extends beyond the barrier. There is a small but non-zero probability of finding it outside at any given moment. Each moment that probability is tested against reality. Most moments it remains inside. Occasionally it does not. The waiting time before decay is therefore not arbitrary. It is set by how far the wave function extends through the barrier, which depends on the barrier's height and width, which depends on the specific nuclear configuration. A thin, low barrier produces a wave function that bleeds through easily and a nucleus that decays quickly. A thick, high barrier suppresses the probability severely, and a nucleus that waits an enormous time before the tunneling event occurs. The range of half-lives this produces, from nanoseconds to timescales vastly exceeding the age of the universe, all falls out of the same mechanism. One equation, one probability. The clock is quantum, not classical, and it was running from the moment the nucleus formed. Tunneling explains how individual particles escape a nucleus one event at a time. But there is a different kind of instability that operates at a larger scale, one that does not involve a single particle finding its way through a barrier, but the entire nucleus losing coherence at once. It becomes possible in heavy nuclei, where the accumulated electromagnetic repulsion has been growing with every proton added, while the residual strong force, limited to nearest neighbors, has not kept pace. In a large, heavy nucleus, the balance is precarious in a specific way. The residual strong force is still winning, but narrowly. The electromagnetic repulsion has been building across the entire proton count, while the binding from pion exchange only ever reaches 1 nucleon deep in any direction. A nucleus like uranium, with 92 protons packed into a space where every one of them is pushing against every other, is not sitting comfortably at the valley floor. It is sitting near an edge. The binding is real, and the nucleus is technically stable, but the margin between held and released has narrowed to the point where a relatively small perturbation can tip it. When a slow neutron enters a uranium nucleus, the perturbation is enough. The nucleus absorbs it, and the added energy causes it to oscillate, stretching into an elongated shape. In that elongated configuration, the geometry changes in a way that matters enormously. The residual strong force, operating only between nearest neighbors, does not change much with the stretching, but the electromagnetic repulsion, acting across the entire nucleus, becomes less offset by the binding as the nucleus elongates. The repulsion begins to win along the stretch axis. The elongation accelerates. The nucleus pinches at the middle and splits into 2 smaller nuclei, releasing the energy difference between the original configuration and the 2 final ones, along with several free neutrons that can trigger the same process in neighboring nuclei. What is released in fission is not energy that was stored in some conventional sense. It is the difference in binding energy between one large nucleus, sitting uncomfortably near the edge, and 2 smaller nuclei sitting more deeply in the valley. The system has moved closer to the floor, and the gap between where it was and where it landed came out as energy. That floor, the deepest point in the valley, the configuration where binding energy per nucleon is highest and the nucleus is most tightly held, is where the next segment lives. Fission releases energy by splitting a heavy nucleus into 2 lighter ones that sit closer to the valley floor. but the valley has two slopes. Heavy nuclei sit on one side, too large, electromagnetic repulsion eating into their binding. Light nuclei sit on the other, too small, not enough nucleons contributing to the residual strong force binding to reach the floor. Energy is released moving down either slope toward the center. Fission descends from one side, fusion descends from the other. Take two light nuclei and bring them close enough to interact. The immediate obstacle is electromagnetic. Two positively charged nuclei approaching each other feel the same repulsion that operates between protons inside a single nucleus, and at the distances required for the residual strong force to engage, that repulsion is a significant barrier. Getting past it requires either enormous temperature, which is the condition inside stellar cores, where nuclei are moving fast enough that some fraction of collisions carry sufficient energy to breach the barrier, or the same quantum tunneling that governs radioactive decay, the wave function of one nucleus bleeding through the barrier into the range of the other. Once past the barrier, the residual strong force takes over, and the two nuclei merge. The resulting nucleus sits lower in the binding energy valley than either of its constituents. That difference in binding energy between the two separate light nuclei and the single merged one is released. In the Sun, hydrogen nuclei fuse through a chain of reactions that ultimately produces helium, and the energy released in that descent toward the valley floor is what has been arriving at this planet as light and heat for 4.5 billion years. Every living thing that has ever existed on Earth has run on the energy of nuclei moving closer to the valley floor. The floor itself is iron, not approximately iron, specifically iron 56, with 26 protons and 30 neutrons, which sits at the precise point where binding energy per nucleon is highest. Nuclei lighter than iron release energy by fusing toward it. Nuclei heavier than iron release energy by fissioning toward it. Iron is where both processes terminate. A star that has built its core up to iron has nothing left to burn. No fusion reaction involving iron releases energy. The core stalls, the outward pressure that held the star against its own gravity disappears, and what follows is a collapse violent enough to forge every element heavier than iron and scatter them across space. The carbon and oxygen and iron that arrived in you came out of that moment, forged in the last seconds of a star that had finally reached the floor. Everything across the last several segments, the residual strong force, the shell structure, the proton-neutron balance, the decay modes, the fission and fusion, all of it maps onto a single curve, binding energy per nucleon plotted against nuclear mass. It is one of the most information-dense pictures in all of physics, not because it is complicated, but because of how much structural necessity it makes visible in a single shape. The curve rises steeply from hydrogen, which has essentially no binding since a single proton has nothing to bind with, through the light nuclei where each added nucleon contributes strongly to the total binding, because in small nuclei almost every nucleon is within reach of almost every other. The rise is rapid, because the residual strong force is getting more nucleons to act on without yet being offset by significant electromagnetic repulsion. Helium-4 sits anomalously high on this early part of the curve, a local peak produced by its magic numbers, 2 protons and 2 neutrons filling their respective shells completely, a configuration so stable it resists being broken apart even inside stellar cores. Past helium, the curve continues rising, but more gradually. The electromagnetic repulsion is growing with each proton added, beginning to eat into the gains from residual strong force binding. The curve is still climbing, because the strong force is still winning, but the margin is narrowing with every step. Around iron and nickel, the curve reaches its peak and flattens, This is the floor of the valley. Binding energy per nucleon is at its maximum. The residual strong force and electromagnetic repulsion have reached their most balanced configuration. Adding more nucleons from here does not deepen the binding. It begins to reduce it. Beyond iron, the curve descends. Heavy nuclei have more nucleons contributing to electromagnetic repulsion than the short-range residual force can compensate for. Each step away from iron toward uranium represents a nucleus holding together, despite a binding energy per nucleon that is lower than iron's, stable enough to persist but sitting above the floor. The curve does not drop sharply. It descends gradually, which is why heavy nuclei can exist at all. But the direction is clear, and the implication is precise. Every nucleus in existence is sitting at a specific point on this curve, and its position on that curve determines everything about how it behaves, what it will do given the chance, and how much energy separates it from where it would rather be. Everything built up across these segments has been pointing toward a revision of the original picture. The nucleus that appeared at the start, dense, persistent, quietly holding at the center of every atom, was not wrong exactly. It was incomplete in a way that the word stable does not capture, and the word dynamic only partially corrects. Consider what is actually happening inside a nucleus at any given moment. The quarks inside each nucleon are in continuous motion, exchanging gluons in a dense, uninterrupted flow, their color charge distribution fluctuating constantly, sea quarks flickering in and out of existence within the nucleon interior. At the nucleon surface, pions are being produced and absorbed in the same continuous exchange that constitutes the residual strong force binding neighboring nucleons together. The nucleons themselves are not sitting at fixed positions. They are occupying quantum states, distributed across the nuclear volume according to their wave functions, moving within the constraints of their shell structure. The entire nucleus is a system in which nothing is still and nothing is where you would point if asked to locate it precisely, and yet from the outside it presents as a fixed, stable, persistent object. The carbon nucleus in a protein molecule does not announce its internal activity. It does not vibrate visibly or radiate its fluctuations into the surrounding chemistry. The dynamism is fully interior, sealed inside the confinement geometry, expressed outward only as mass and charge and the occasional decay event when the balance tips past a threshold. The stability is not the absence of motion. It is the precise cancellation of motions that individually would be catastrophic, held in balance by constraints that operate simultaneously at the quark scale, the nucleon scale, and the nuclear scale all at once. This is what makes the nucleus unusual even within physics. Most systems can be understood by focusing on one scale at a time. The nucleus cannot. The color confinement that operates between quarks directly determines the mass of the nucleons that the residual strong force then binds, which determines the shell structure that governs which configurations are stable, which determines the decay behavior that defines where on the binding energy curve a given nucleus sits. Pull on any one layer, and the others respond. The nucleus is not built from the bottom up in a way that allows the layers to be understood separately. It is a single integrated system whose behavior at every scale is entangled with its behavior at every other. Step back from the individual mechanisms for a moment and look at what the binding energy curve is actually saying. Not the shape of it, but what it means that such a curve exists at all. That every nucleus, from hydrogen to uranium, can be placed on a single line, ordered by how tightly bound its nucleons are, and that the position of each nucleus on that line is not arbitrary, that follows directly from the interplay of everything described so far. A curve like this is what emerges when multiple competing constraints operate simultaneously across the same system, and each nucleus represents a specific resolution of those constraints. The residual strong force pulls nucleons together with a range limited by pion mass. Electromagnetic repulsion pushes protons apart with a range that is effectively unlimited. Shell structure creates discrete preferred configurations that sit lower in energy than their neighbors. The proton-neutron balance requirement carves a narrow path through nuclear composition space. Each nucleus is sitting at the intersection of all of these simultaneously, and the binding energy per nucleon is the single number that summarizes how well that particular intersection works. What the curve makes visible is that the universe has a preferred scale for nuclear matter, not an atom, not a free quark, not an arbitrarily large nucleus. A nucleus in the vicinity of iron, where the competing constraints balance most efficiently, where the residual strong force is getting the most binding per nucleon relative to the electromagnetic cost of assembling that many protons in one place. Everything lighter is moving toward that scale when it fuses. Everything heavier is moving toward it when it fissions. The curve is not just a description of nuclei that happen to exist. It is a statement about where nuclear matter naturally wants to be, and the distance any given nucleus sits from that point is a precise measure of the pressure it is under. That pressure is not metaphorical. It is the actual energetic difference between where a nucleus is and where the constraints would place it if given the chance. For stable nuclei, that chance never comes, or comes only across timescales that dwarf the age of the universe. For unstable ones, it comes sooner, through the mechanisms already described, each one a different path down the same slope toward the same floor. The curve unifies all of it, one picture, every nucleus, every decay mode, every fusion reaction, every fission event. All of it is motion on this curve toward iron, and the energy released in that motion is what has been powering the universe since the first nuclei formed. There is something worth sitting with before the final layer. The nucleus that appeared at the very beginning of this, the dense, persistent cluster forged in stellar cores and sitting unchanged inside your body since before this planet existed, has not been replaced by everything described since. It has been filled in. The persistence is real. The stability is real. What has changed is the understanding of what that stability is made of. Before this descent, the nucleus was a black box with known properties. It held. It had mass. It had charge. Occasionally it decayed. Those were the observable facts, and they were sufficient for most of what chemistry and biology needed from nuclear physics. The box did not need to be opened for a protein to fold or a chemical bond to form. The nucleus sat at the center of the atom and did its job quietly, and nothing about the job required knowing what was happening inside. But the inside is where the physics lives. The color confinement that permanently imprisons quarks is the same mechanism that gives nucleons most of their mass, which is to say, it is the mechanism responsible for most of the mass of everything you have ever touched or lifted, or felt the weight of. The residual strong force that leaks through color-neutral nucleon surfaces is the only reason nuclei larger than hydrogen exist at all, which is to say, it is the reason every element except hydrogen exists, which is to say, it is the reason chemistry has more than one actor. The shell structure that determines which nucleon configurations are stable is the reason the periodic table has the shape it does, rather than being a smooth, continuous distribution of equally stable nuclei. These are not details sitting underneath observable reality. They are the structure that observable reality is built on. What the nucleus is, stated as precisely as everything here allows, is a system in which the most fundamental forces in nature operate simultaneously at the same scale, each one constraining the others, their combined effect producing a stability that is not passive but active, not given but continuously maintained, not a property of the nucleus but an outcome of everything happening inside it at once. The solidity you felt at the very beginning, running a hand across a surface, was always this. It was just waiting to be opened. There is a habit of thinking about the fundamental forces as separate chapters in a textbook. Gravity gets one, electromagnetism gets another. The strong force and the weak force get theirs. Each is introduced with its own carrier, its own range, its own cast of particles, and the impression created is of four distinct mechanisms that happen to share a universe without deeply informing each other. The nucleus is where that impression breaks down most visibly. Inside a nucleus, three of those forces are operating simultaneously at the same scale, and the behavior of the system cannot be understood by considering any one of them in isolation. Remove the strong force and the electromagnetic repulsion tears every nucleus with more than one proton apart instantly. Remove the electromagnetic repulsion and there is no upper limit to nuclear size, no binding energy peak, no valley of stability, no periodic table as we know it. Remove the weak force and there is no mechanism for adjusting the proton-neutron balance, which means the valley of stability narrows to a line, and most of the nuclei that currently exist would not. Each force is not just present, each one is load-bearing. The structure depends on all of them being exactly what they are simultaneously. This is what makes the nucleus more than a topic in nuclear physics. It is a place where the architecture of physical law becomes directly legible. The specific value of the pion mass sets the range of the residual strong force, which sets the maximum size of stable nuclei, which sets the heaviest elements that can exist, which set the range of chemistry available to the universe. A slightly different pion mass and the curve shifts. The valley moves, the stable elements change, and the chemistry that produced every living thing becomes unavailable. The nucleus is sensitive to the values of the constants that govern it in a way that propagates directly upward into the existence of complex matter. And at the bottom of all of it, underneath the shell structure and the binding energy curve and the decay modes and the fusion reactions, are quarks that have never been seen in isolation and never will be. Permanently confined, invisible individually, detectable only through the composite objects they are locked inside. The nucleus is built from constituents that cannot exist outside it, held by a force whose carriers are subject to the force they carry, producing a stability that is active rather than passive, dynamic rather than inert, and old enough that the structures sitting inside you right now were forged before the Earth existed. That is what the nucleus is made of, not particles sitting still inside a boundary, forces in conversation, constraints in balance, and energy that has nowhere else to go.